Now that we have a little bit of background in factorials, we want to move on to talking about permutations and combinations. We'll start here with permutations. And the thing to remember about permutations is the word position. So when you think permutations, think position or order or arrangement. In other words, order matters, or the position of the items matters. Now, you might be wondering, we just talked about factorials, and we said that a factorial represented an arrangement. So the question then becomes, how are permutations different than factorials if factorials represent an arrangement? Well, if you remember before when we talked about factorials, we did an example where we talked about the playing cards. We had a king, a queen, and a jack. We had 3 face cards. And in the context of factorials, when we talk about the number of ways in which we can arrange these 3 face cards, we have 2 limitations. The first limitation is that we have to arrange all 3 cards in our set. In other words, we have 3 face cards, we have to arrange all 3 of them. We didn't address what it would mean to have 3 face cards, but only want to arrange 2 of them. Because as you can imagine, if we only want to arrange 2 of these, but we have 3 that we can pick from, we could look at all the arrangements with the king and the queen, but we could also look at arrangements with the queen and the jack, or we could look at arrangements with the king and the jack, and the number of ways in which each of those subsets can be arranged. And when we talked about factorials, we also didn't address the possibility of repeats. So when we had this king, queen, and jack, we only imagined a scenario in which we could arrange 1 king, 1 queen, and 1 jack. But what if we have a whole deck of playing cards, and we therefore have the possibility that we could arrange 1 king, 1 queen, and 1 jack, or that we could keep repeating. We could have king, 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 or queen, jack, queen. In other words, we can repeat a card, and we still want to know the number of ways in which we can arrange that set when the order of that set or the order of that arrangement still matters. So now that we're introducing permutations, we're going to be able to address both of those things. And what we're going to be working toward is filling out this table right here. We're going to start by looking at permutations, so we're going to start by working on this top row. Then later on, we'll look at combinations and we'll fill in this bottom row. And within each one of these rows, when we talk about permutations, when we talk about combinations, we're going to talk about how to calculate the number of permutations or the number of combinations when we can repeat items in the set versus when we can't repeat or when repeats aren't allowed. So to start building out this table, let's go back to our king, queen, jack example from the factorials lecture. If you remember, when we had 3 face cards and we wanted to arrange all 3 of them, we said that the number of possible arrangements was going to be equal to 3 factorial because we had 3 items in the set. So in other words, given n items, the number of arrangements was n factorial. And if you remember, when we did that calculation, we said that the order mattered. We said that the arrangement king, queen, jack, for example, was different than the arrangement king, jack, queen. So because the order mattered, when we calculated that n factorial value, we were actually calculating a permutation. In other words, in the last lecture, instead of saying that we were talking about factorials, we could have said that we were talking about permutations. We were just forcing the arrangement of the entire set instead of allowing for subsets of the arrangement. When we allow for subsets, we use a different formula, and that formula is the one that we'll put here. It's n factorial divided by quantity n minus k factorial. And the idea here is that we have n number of items in our set, and we're choosing k of them to make permutations. So for instance, if we start with 1 king, 1 queen, 1 jack, we have this set of 3 items. Then in this case, n equals 3. And let's say we want to determine the number of ways in which we can arrange just 2 of these cards. In that case, k equals 2. So what we're doing is we're starting with this set of 3. We're picking just 2 of these 3 items. So we could pick the king and the queen, we could pick the queen and the jack, or we could pick the king and the jack. So we're picking 2 first, and then once we have our set of 2, we're calculating the number of permutations, the number of ways in which we can arrange that set of 2. So for instance, if we picked the king and the queen, we know we could arrange that as king then queen, or as queen then king. So of course, if we plug that into this formula here, we're going to get n equals 3 factorial divided by n minus k, or 3 minus 2, so 3 minus 2 factorial, and the result here is 3 factorial over 1 factorial, or 3 times 2 times 1 in the numerator is 6. 1 factorial, of course, is just 1, so we get 6 over 1, or 6. Now what happens if we start with this same set of 3, king, queen, and jack, but we only want to choose one of the cards? In that case, n equals 3 and k equals 1, and so we would end up with 3 factorial divided by quantity 3 minus 1 factorial, or 3 factorial over 2 factorial, in which case we get 6 divided by 2, or 3. And that should make sense, because if we're only choosing one card from the set to arrange at a time, then we're either choosing the king, and there's only one way to arrange that, we're choosing the queen, and there's only one way to arrange just the single queen, or we're choosing the jack, and there's only one way to arrange just that single jack. So there's 3 ways to arrange. There are 3 permutations if we start with a set of 3 and we just pick one item at a time. Or to pick an entirely different example, if we're trying to figure out the number of ways in which we can seat 5 people around a table, and in this case, maybe order really does matter to us, maybe we really do want the permutation, because we care who sits next to who. Well, look what happens if we arrange all 5 people. Using this formula, because we want the number of permutations, order matters to us, we care who sits next to who. But of course, we're dealing with people here, so we can't repeat them. We can't have the same person sitting in 2 different seats. So we're looking at the number of permutations with no repeats. We can use this formula. If we want to arrange all 5 people around the table, then both n equals 5 and k equals 5. We have n equal to k, and we would set that up as 5 factorial divided by quantity 5 minus 5 factorial, or 5 factorial over 0 factorial. That denominator always goes to 0 factorial when n is equal to k. We know that 0 factorial is equal to 1, which means this simplifies to just 5 factorial. And remember, we said we had n equals 5 people, so this is really just n factorial, and we're back to this factorials idea. Remember earlier we said that factorials were just like a permutation, except that we always used the entire set. Well, here, that's just what we did. We had 5 people, and we wanted to arrange the entire set of all 5 of them, instead of some subset like just 3 of the 5 people. So with 5 people, when we want to arrange all of them, but order matters, so we're finding a permutation, this denominator always simplifies to 0 factorial. We always get n factorial. So when you think about 5 people and you want to arrange all of them, that's this formula here, but you know that's just going to simplify to n factorial. So in this case, we know 5 factorial is 120. There are 120 ways to arrange 5 people around a table. So that's how the idea of permutations and factorials are related to one another. Let's just fill out this one last box here, permutations, where we allow for repeats. So an easy example, or an easy way to think about this, is with phone numbers. So let's say we want to figure out how many 7-digit phone numbers we can make. Well, if we use all the digits 0 through 9, so 0, 1, 2, 3, all the way up through 9, that's 10 digits. If we had started with 1, we would have had 9 digits. 1, 2, 3, 4, all the way up to 9 is 9 digits. But when we add in the 0 as a digit, this is 10 digits. And if we're allowing repeats and making a phone number with 7 different digits, then think about it this way. When we pick the first digit, we can pick any one of these 10 digits. So we have 10 possibilities for the first digit of the 7-digit phone number. So if we say 1, 2, 3, and then 4, 5, 6, 7 for our 7-digit phone number, we have 10 possibilities here. When we go to pick the second digit, of course, we're allowing repeats. We can use the same digit again in the phone number, so we again have 10 possibilities. And this is always the case. We'll have 10 possibilities for every digit in our 7-digit phone number, which means that when we allow repeats, the calculation we use is simply n to the power of k, where n is the number of things we have to pick from, in this case, 10 digits, and k is the number of times that we're making that pick. Here we picked 7 times because we had 7 spots to fill to make a phone number. So we're picking from 10 things, we're picking 7 times, which means that in this phone number example, the number of phone numbers we can build is given by 10 to the 7, which is equal to 10 million. So there are 10 million 7-digit phone numbers that we can make if we allow ourselves to use all 10 digits 0 through 9 and repeat them as many times as we want. meaning we can start with the phone number 0000000 and go all the way up to the phone number 9999999, but the order of the digits matters, which of course makes sense because the phone number 1000000 is not the same as the phone number 0100000. The place where we put the 1 changes the phone number. So order matters. We're dealing with a permutation. We have 10 digits to pick from every time, and we can make 7 picks. That calculation, permutations with repeats allowed, is n to the k, where we pick from n items k number of times. So that's how we calculate permutations. And in the next lecture, we'll compare this to combinations and learn how to calculate combinations with both repeats and no repeats.